All right, looks like we're gathering. We'll take just 1 or 2 minutes before we get started, but I want to welcome everyone to our Data Science Fridays seminar series. I'm delighted to see so many of you here again today. Really exciting seminar today by Sakshi Misra from the National Renewable Energy Laboratory. I'll talk a little bit about Sakshi and then introduce her seminar, and then we'll get started. So welcome everybody. And there's Lizzie Fink. Hi Lizzie, great to see you. Sakshi is an energy researcher, a power systems engineer, and a machine learning practitioner. She's interested in working on enabling large-scale clean energy integration into the smart grid by using artificial intelligence-based methodologies. At NREL, she is working as a development lead for the REopt Lite API and its open source effort. She's also part of NREL's Intelligent Campus project, where she leads predictive analytics research and development using machine learning. Before joining NREL, Sakshi was a transmission planning engineer at American Electric Power, where she served as an industry advisor for PSERC projects. She holds a professional engineer license in the state of California and a master's degree from Carnegie Mellon University in Energy, Science, Technology, and Policy, and received her bachelor's degree in electrical and electronics engineering from VIT University in India. And she conducted her bachelor's thesis as a full ride scholar at Deakin University in Australia. So today I'm really delighted to have her join us in our community today. The title of her talk today is Data Science and Optimization, REopt Lite. Sakshi, welcome.
Thank you, Gwen. So without any further delays, we'll get started. I'm gonna share my slides real quick. Okay, so thanks again for having me here today, and thanks for the introduction, Gwen. So today's talk will be about data science and energy systems. And energy systems, as you know, are one of the major sources of CO2 emissions, and they're very much important in our everyday life too. So these days, it's getting more and more important to understand how can the carbon emissions in the energy systems can be reduced. And there are so many opportunities in there to apply data science to help energy systems get more efficient in general and reduce their carbon emissions. So with that theme in mind, I'll be talking about tool from National Renewable Energy Laboratory, which is called REopt Lite, which is an optimization tool, which takes a bunch of data and processes it and gives the recommendation for installing renewable energy technologies on the site. So what data does it take and how it does that is something I'll be discussing as we go. So in terms of agenda, I guess I'll take a minute or two to talk about my profile, and I like to talk about it because it's my path to data science has not been a straight line. So the message I try to get out usually is that even if one has not started in computer science field as their background in their bachelor's or master's, there are many ways to still get into the field and use it and then fuse it with the other background which you have had in the past, maybe electrical, chemical, mechanical engineering, because today there is a lot of need for such professionals who have background or expertise in specific area, but they are also having enough data science skills so that they can apply data science onto that field. So after that, I'll give a quick baseline to think about optimization and related to machine learning a little bit before we dive into energy systems and smart grid. And then it will be a description of the REopt Lite tool, which is again an optimization model, and a few thoughts on diversity and inclusion, and then Q&A. So about me. My bachelor's was in electrical electronics engineering, then master's was in energy science, technology, and policy from Carnegie Mellon. Then professional certificate from Stanford in energy innovation and energy emerging technologies. And I'm currently continuing my PhD at University of British Columbia as well. And I have a PA license from electrical engineering from the state of California. So my background has been, so the diagram you see here is of energy systems. It's pretty common, the notion of how energy systems are as overall high level. So there is this black part where there is centralized generation going on. Then there's this blue part where the power generated is stepped up, its voltage is stepped up, and then transmitted through long distances. Not so much in Hawaii, but like United States mainland, where geographically diverse and huge areas. So transmission lines basically carry a lot of power on high voltage with the goal of keeping losses minimum by increasing the voltage. And then the green part is the distribution grid, where the power is stepped down and brought to a little lower voltage. And then the black part toward the right is the consumers. So I have a kind of work in, I have had experience, or I was fortunate to have opportunity to work in different parts. When I was in Deakin University, Australia, it was about microgrid, and how setting up a test bed. And it, jumping back to NREL, my current role, where I'm doing solar forecasting for PV generation plants using deep neural networks. And then at AEP, another company I had worked in transmission part. And then distribution engineering, that's where a lot of data science focused work was. It was at Black Beach when I was interning there. So it was machine learning was used for feeder level analysis and different types of visualization. T-SNE is one of the visualization algorithms, and then using linear regression for energy consumption predictions. Those were some applications of data science which I had worked on. And here at NREL, REopt Lite tool, which I was introducing earlier a little bit. And now at University of British Columbia, I'm involved with the blockchain for smart grid and reinforcement learning. So yeah, my background has been kind of diverse, but the theme which I have been holding on to is energy systems, their different parts, and how do I bring in data science-based solutions to make them work better than how they have been working traditionally. So with that, super quick primer to optimization, I guess. And then, so optimization essentially is about, there are three components to it. So one is objective function. The first one is objective function, which is, this is a set of goals towards which the algorithm drives the solution. For machine learning, for example, often this is the amount to minimizing some error measure or maximizing some utility function. So usually machine learning, supervised machine learning as an example, what is happening behind the scenes is we get the training data and train the algorithm, and then somehow it figures out, the neural net, for example, figures out the right parameters to minimize the loss and be able to predict the target better. But the loss minimization, how it happens is through optimization. That's what is happening under the hood. And then, so these three components, objective function, then there is decision variable, which is, these are the free parameters which the algorithm tunes at the, as its goal. And then constraints are the boundaries within which the parameters should fall. So formulating that as an optimization problem helps minimize the loss function, which as a result gives us the parameters which help the model train itself better and better to be able to predict to reasonable accuracy. So this one plot shows like how this is the decision space and how these different optimizers, SGD, momentum, and all these are different types of optimizers you might be knowing about it, which are available for training deep neural networks or neural networks. So this is the problem space of how the optimization happens for them to reach their global minimum. So it wouldn't be an overstatement to say that optimization is at the heart of majority of the supervised machine learning methods. So with that quick primer in mind, let's dive into the smart grid realm. So energy systems, smart grid, and smart grid term has been around for more than a decade at this point, but it's not old because so many new innovations are coming into picture every new day as technology is progressing. So there is this technology pull, but there is also this climate change push or market push where there are goals being set and the targets for reducing the emissions require more and more innovation in energy systems field, for which there are multiple things which are happening in smart grid domain. So if we think about the main drivers of it, one way to characterize them or to categorize them would be, one is because of climate change problem, there is a push to integrate more and more renewable energy into the grid. But as more renewable energy is integrated into the grid, the nature of renewable energy is such that it is intermittent in nature. So how can grid take that kind of unpredictability into account and still be able to maintain the supply and demand at the same times equally? That's something, it poses a bunch of challenges which need to be solved. Then there is another driver, which is transportation electrification, for example. So more and more EVs, and it's predicted, the market is predicted to grow even more in the coming decade. So let's say 60% or 70% of vehicles are converted to electric vehicles, then they are going to charge from the grid. They can sell back power to the grid. So that's another driver which is causing this rapid change. Then aging grid infrastructure is also another reason that, for example, in US, the grid is now a century old, and in California, there have been many cases where if a tree falls down, then if a distribution grid's tower is old, then it takes away the power, blackout happens. And so that's another reason that it's important for utilities to maintain or upgrade the infrastructure. So that's where there is, again, room for innovation. Same way there are grid interactive buildings. So built structures are growing, urbanization is happening. So more built structures means more energy requirements, which turns to more emissions. So innovation there required too. And then this technology push where there is proliferation of connected devices, Internet of Things, where with our smartphone, we can turn the washer off, dryer on, and all sorts of controls we have gained. So how the orchestration of all these factors together are pushing toward need for more and more innovation in the energy systems and smart grid domain. And so that's where data science can play a big role. And so when I say smart grid, it's a bunch of technologies coming together. It's control centers, it's buildings on one side, there are central big utility scale generation plants, then there are distributed energy resources which are on top of buildings, and small scale close to the consumer, and these DERs, distributed energy resources, they are there. Then there is renewable generation plants, and then there is base load of fossil fired plants. Though eventually we want to get rid of all the fossil fuel fired generation, but right now majority of our electricity is today coming from fossil fuel based sources. So they are part of smart grid even today. And then cities and buildings which are getting more and more sensors and measurement devices installed onto them, so thereby getting more intelligence. So they're also part of smart grid. So this is like a tightly knit cyber physical system orchestrating operations of all these things coming together. So smart grid, the point here is it has a lot of room for data sciences applications, which can make it work better and address the current challenges which are being faced. So I think a handful of application examples would be: one is improved accuracies of renewable generation predictions. So as I was explaining earlier, that renewable generation sources are intermittent in nature, inherently. That's how they are. Sun shines on solar panels, and if there are clouds were to come for a few minutes, so generation is going to drop. Same way with the wind. If wind stops to blow, the turbine won't rotate, which means the power generation is going to drop. So the ability to predict the generation in the coming few minutes, few hours, and day ahead, and the accuracy with which it can be predicted can help a lot for grid operators to actually be able to plan it well, because essentially grid operators, they plan ahead sometimes. Like there are different time scales they do it. One is for hourly planning, then there is day ahead planning, where they go out and ask generators to give their bids that this much power I'll be generating, I'll be able to generate and inject into the grid for this time. But for renewable generation technologies, if they're not able to come up with good predictions, then it gets harder for them to give a number, and for harder for grid operators to actually manage the grid in real time when the predicted generation is not getting fed into the grid. So neural networks, recurrent neural networks, for example, their application is very much relevant here, which can help increase the accuracy. Then there are enhanced controls to effectively manage the power flow on the grid. So previously the power flow used to be just one directional. Utility plants, big plants will be producing the power, and it will be sent to the load centers or consumers where it's being consumed. But today, with distributed energy resource installment, and it's growing, their penetration is growing. Again, it's a bi-directional power flow. Loads consume the power, our houses consume the power, but if we have a solar panel and it is generating at its peak during the afternoon, and we are not really using all that power, it gets actually fed back to the grid. So there are regulatory concerns, so many things surrounding that, but at the end of the day, if the bidirectional power flow has to happen, then the controls capability of the grid needs enhancement. So reinforcement learning, for example, could be applied in this domain to help get better controls in there. Then another application is predictive maintenance to avoid equipment failure related outage. So as I was mentioning earlier, grid is aging. It's a century-old grid. So parts here and there get replaced, and there are schedules to check them and then replace them. But still, at times, and actually many times, it happens that unexpected equipment failure. So once the equipment fails, then it takes a lot of time to replace it or repair it, and that which converts to customers not getting the power outages. So that can be avoided if machine learning algorithms can be used to predict the failure, or predict that this component needs maintenance beforehand. So accordingly, the power flows can be, the grid operator can decide that, okay, that transmission line is gonna be out for a week in the month of February next year. So let's plan how can we get the power delivered to the customers through a different route. So being able to predict the maintenance for such all the equipment on the grid helps tremendously with maintaining the reliability of the grid. Then there is this question of resilience. So these days, because of climate change, we see extreme weather events happening more frequently than they used to happen before, which means that if one component in a large power system goes away, and let's say that was a critical component, or it didn't have a redundant or parallel component where power can be rerouted, which means the grid is not resilient, and now a big chunk of customers or houses get disconnected from the power for days at times, if it's a big calamity like a hurricane or earthquake or things of that sort. So resilience is something which really needs to be built within power systems. So building operational resilience, machine learning can help, data science can help a lot there in actually intelligently defining that, okay, if that equipment is out or if that were to go out, how can we build the plan to get the power rerouted to the customers or consumers when that equipment were to go out, or how can we safely just cut only 10% of the consumers and still be able to serve remaining 90% by reconfiguring our system in in a certain way. So that's where data science comes in and can help a lot. Then there is shared vehicle infrastructure use. So as EV penetration grows, the infrastructure for charging is growing and it's getting built. Currently, it's in process. So once it reaches a point where the electric vehicle penetration has grown a lot, then there will be questions like, we expect to have some sorts of apps which can guide us that, okay, this is a good time for you to charge your vehicle. Tell us your preferences. We can tell you your charging infrastructure where you don't have to stand in a queue for longer. So that also needs a lot of help from data science to be able to get process all the data about where vehicles are, what are the capacities of the different charging stations in the vicinity, and what's the shortest distance to get there. All those questions needs to be solved, and data science can help there too. And same way, better insight into the operational conditions of the system. So in power systems, because of decreasing cost of measurement devices and sensors, more and more of them are getting deployed all over the grid. So there is data, a lot of data which is getting gathered through those sensors. So drawing insights from that data to be able to understand the operational condition of the system, a lot of use of data science there is. So I think to summarize, energy systems are transforming. A lot of changes are happening, and there is a need for professionals to go in and help out with data science skills, to go in and help out with making this transition happen and bringing in more innovative solutions. So with that, I will move to the next part, which is REopt Lite, which is one of the tools, optimization-based tools from National Renewable Energy Laboratory, which solves or which answers the question that, is it economically feasible to install distributed energy resources on a resource on a given site, which is located at a given geographic location. So it helps answer a bunch of questions. So is it economically feasible to have a renewable energy and storage system installed on your site? So such a question, this is a decision science question. It involves a lot of factors that given the geographical location of your place, if it's in let's say East Coast and up north, the sun may not shine as bright as it would in Hawaii or Denver. So that's one factor. Then technology costs and incentives. So cost of technology has been constantly decreasing, especially renewable energy technology. So at what point does the capital cost which we invest in getting it, in buying the technology and getting it installed, evens out with the savings we will get? Then resilience goal, given these situations of extreme events, if centralized power or grid were to go out, how many hours do we expect our system to sustain our house load? Then utility cost and consumption. So there's a variety of tariff options available for users to choose from. So how do those tariff costs change the economics of whether it makes sense to install a distributed energy resource or not? So REopt takes all those factors into account, and it's a better, this diagram gives a better presentation of what goes as input. So REopt considers technologies like solar PV, wind, conventional generator, batteries, and then that's a user input. And based on this input, I say, okay, I want to see if PV plus battery makes sense for my house. So those will be the inputs I'll provide. And then it takes the drivers into account, cost minimization being the primary driver, which is the objective function of the optimization problem. And then resilience goal, that these many hours our system should at the minimum survive if the grid were to go out. Then drive economic drivers such as technology cost, incentives, and financial parameters. And then also utility tariff cost, which again has multiple components to it: energy charges, demand charges, escalation rates. And given these drivers and these technology options, REopt runs a mixed integer linear program to determine what is the optimal technology mix for a given site, and what are the sizes. So mix could be solar and wind, or solar or PV, or wind or storage. So determining that mix and its size, as well as optimal dispatch over one full year, that if your assets or your generation technologies, distributed energy resource generation technologies, were to be dispatched in this way over the year, this will minimize the cost. So that's in a nutshell what REopt does. So it can answer questions from different perspectives. So one is, what is the optimal size of DERs? That was the example I was discussing, to minimize the cost of energy. Then from a grid operator perspective, if they want to understand how do I optimize the system control across the multiple value streams to maximize project value, that's another question it can help answer. Then the question of, where do market opportunities for DER exist? So if we have distributed energy resources installed on our site or roof, and then we are able to sell it back to the grid because of excess production that then what we are consuming, then where it is best. So it's not from, I think, a home owner perspective, it's more like developers who are developing DER behind the meter distributed energy resources. Where should they place them? So it helps answer those questions. Or sometimes, what is the most cost-effective way to survive a grid outage? So it ties back to the resilience goal, that if we wanted our system to be able to survive, let's say at least for 3 days, if grid power were to go out, then how do we size our system? And if we were to size our system that way, how is economics playing out? So it does the optimization to make optimal recommendations of the technology sizes for that. So how does it work? So it's essentially considering the trade-offs between the ownership cost or the capital cost, capital plus O&M, and savings across multiple value streams. So when it says do optimal dispatch, what it is trying to do is energy arbitrage. Buy the energy from the grid, store it in your battery, and then when it's cheap, and then use it to serve your house load when the energy is costly from the grid. So that's one of the ways it's trying to minimize the cost there. Then demand reduction. So I was mentioning earlier that utility has different components: energy component, demand component in its charge tariff structure. So if we are able to bring down the demand component, or if we are able to bring down the peak of our consumption, then it saves amount or money. So REopt helps determine how to reduce that peak by utilizing on-site storage as a part of the DER strategy. So that's how it helps figure out whether it makes economic sense to install a distributed energy resource or a clean energy technology onto your system. So here is the data science part to it, that it's running an optimization model under the hood, which is a mixed integer linear programming model. So it's a mixed integer linear program because there is one sets of variable which are binary variable, whether to install a technology or not, which is 0 or 1, and then there is continuous decisions of if yes, then how big a size will make the economic sense to be installed. So that's how it becomes a mixed integer linear program. The mathematical model written in it is in Julia, or JUMP programming language. Julia is a little new programming language, but its optimization package, which is JUMP, is pretty efficient. So that's the one which REopt code has been recently converted to. Previously, it was using another programming language called Moselle for coding the optimization part, but it's been changed to Julia JUMP recently. Then there are pre-processing, and lots of data pre-processing happens. So the data which gets fed to it is like the load profile, time series, hourly time series for the whole year. Then the solar generation profile, that for this geographic location, how much solar resource is expected for the coming year. Then similarly, wind generation profile, that's get fed. Then utility tariff, which varies across time of use, and then demand tiers and energy tiers. So it ends up being a matrix of data, the utility tariff itself. So given all that, that's the kind of data which goes as input to it. Then with significant, so REopt, yeah, it's been under development at NREL for more than a decade, about 12 years now. So lots of modifications our team does for to answer the questions, variety of questions with it. So what it is doing is solving energy balance at every time step for the entire year. So if it's hourly, then it's gonna be 8760 data points in the time series. And if it's sub-hourly, let's say 15 minutes interval, then it's gonna be 35,040 data points per time series. So how it solves is that load must be met from a combination of grid purchases, on-site generation from DERs, or discharge from the storage. It's a behind the meter energy optimization model, so it does not consider the power flow. It has perfect prediction about upcoming weather and load events, and it assumes 20 to 25 years of total project cycle to actually does the economic, do the financial and economic calculations of whether it makes sense to install it over the whole life cycle of the project. So little more details about optimization model. So the technology modules are based on empirical operating data. It finds optimal technology sizes, which could be 0, and optimal dispatch strategy subject to the resource, operating, and goal constraints. I think I mentioned it before that the objective function is minimizing the life cycle cost of energy, and it resulting life cycle cost is guaranteed optimal within a known gap subject to the modeling assumptions. So in terms of its formulation, its overall cost minimization, then decision variables are technology types, which are binary, and then dispatches, which are continuous. And then in terms of constraint, it considers a bunch of them. So it's system sizes, load constraints, production constraints, fuel tracking constraints, then storage constraints. So yeah, it's like lots of technical or physical constraints associated with the system which is getting installed. It does consider them all to come up with the optimal decision for sizing the technology. In terms of ways to work with REopt, there is an internal model which is pretty comprehensive. It has lots of features, and it's been in development for 12 years. Then REopt Lite is a web tool. It's actually pretty, do check it out if you're interested. So it's like a web, just a website with a form. 4 or 5 inputs are necessary, and they're pretty easy. It's just a geographic location and load type and couple more inputs which are mandatory, and there are tooltips in there which helps filling it out, and then it runs the optimization under the hood and then shows the visualization of how the technologies can be dispatched, and then outage simulation if resilience of the site is being studied. Then it's also available as application programming interface, and this year we open source its code base, so that's also available if you're interested in looking at how does the optimization model works under the hood of the web tool. So in terms of REopt's summary, it's an optimization model which is facilitating answering complex questions about system design and dispatch, with the goal of informing people about can they install distributed energy resources, meaning would it be economically viable to install them. The results are driven by economic objective, which is minimizing the cost. The model determines which technologies to add and how to operate them to satisfy the objective of cost minimization. Size, technology mix, and dispatch is not a user input, but a model output. So model helps decide, or model recommends the sizes and technology mix. The user is able to force in a technology type if they want it by setting the constraints. So there are constraints in there that which could be, I want minimum of 50 kilowatts PV to be designed in the system which is being recommended. And REopt model takes care of that constraint while finding the optimal solution of the problem. So I think this was one such application of optimization in energy systems. With that, I will move on to one thought which I always like sharing whenever I'm, even if it's a totally technically oriented talk. I think a matter of diversity is not just for, I think, human resources, but it's more for all of us who are working in STEM field, or who are studying and who are planning to work in STEM field. It's always important to keep in mind that STEM needs diversity. Percentage of female here in the United States, back in India, all over the world, actually, if we read the statistics, it's always less. And it has to reach like parity at some point, right? So that needs, as a society, or as people like us who are working in STEM fields, we can encourage young girls, little girls to dream to study in this field, and also understand that human minds, it's like lot of untapped potential in there if we are just not able to harness it because of diversity issues, or color of the skin, or race, or gender, or all those biases. It's not helping. So something for us, I guess, as STEM people working resources in STEM, is to keep in mind that whenever we get a chance, it's always good to encourage everybody who seems somewhat interested, or even sow the seed of interest within them that STEM is a promising career for anybody who wants to do that. So with that, I think I'll get to the key takeaways today. So energy systems are at the verge of transformational change, and climate change is kind of at its root. It's driving all those changes. Then data science, be it machine learning or optimization, or them together, have the capability to bring about tremendous positive change in the way electricity is produced, transmitted, and consumed today. Because the goal really is to be able to bring down the carbon emissions. But that doesn't mean that we can stop using electricity. We have to. It's a very basic human need today to have electricity. And developing economies, their energy needs are going to grow over the years as the economic developing nations' economy gets better and better. So the only way really is to figure out how to more efficiently generate using clean energy resources, more efficiently transmit and use the energy more efficiently. So like figuring those ways out needs a lot of innovation, and that's where data science has a big role to play. Then another takeaway is that one doesn't need to be like knowing energy systems or knowing only data science. Like professionals from different backgrounds are needed to come together and make a team to work on it. One can have expertise in energy systems, other one can have expertise in mechanical systems, and then data science professionals can have expertise in data science, and they can all come together to actually brainstorm the solutions which can be built to make energy systems more efficient. And last but not the least, that diversity. Yeah, I think I have discussed it just a few minutes before, but it's something I feel that there is a huge human intellectual potential. It's human brain, and if there is willingness within the human being, then it's like from a business point of view, it's a loss that such a human potential is not getting tapped within STEM field because of diversity or like because diversity is not getting celebrated. So it's something, yeah, I think lots of efforts out there which are happening, and things are changing, and hopefully they'll change faster and we'll see more and more diversity as we go. So I think with that, I will take any questions.
Hey, thank you. That was a wonderful seminar. I think folks can either raise their hand or type a question in, or just go for it. We have a friendly group here. Anyone have a question? Actually, Sakshi, I have a question just to start out with. When I was reading your bio, I noticed that you have a master's degree in energy policy. Can you talk a little bit about how that's kind of shaped your career path and the projects that you work on now? I thought that was really interesting.
Yeah, so actually it was like an interdisciplinary degree. So energy, science, technology, and policy was named. So I had like a couple of courses where they were really just talking about the policy issues. So coming from a technical electrical engineering background, it really did help me open up my mind about how it's not just, solutions cannot be purely technical. Like unless a policy component is at it ends up being something just published as a research instead of like actually getting deployed. So that helped me, that informed me to think whenever I was coming up with technical solutions, always think from the angle of, will it make sense from policy people's perspective? So I think that's how it was helpful.
Oh, wow, very cool. Okay, who else has a question? Any other questions for section today? Nothing here. Someone must.
Sakshi, I was wondering if you could say anything more about predicting solar power generation using deep learning.
Sure. So I have worked on it in the past, and what I used was recurrent neural network and then LSTMs. I guess I'm getting too much into just the technical part. Maybe I should talk holistically about it. So it is essentially solar energy generation prediction depends on weather prediction. So largely the models which utilities utilize today are, they take the weather predictions and those predictions are used as input to the models which predict the solar generation. So which is okay, which has been working, but accuracy can be improved further if we try and remove the component of weather prediction. So the work I did before was like taking measurements of meteorological variables like humidity, temperature, and few more such variables. But from this time and and then T-1, T-2, T-N, and then try and predict solar resource based on that. So what I was doing was taking away the part of weather prediction, which brings in more uncertainty in the equation. So that helped increase the accuracy quite a bit. So that's like the input output part of it, and the algorithms which I use were RNN and LSTMs with PyTorch library implementation. Was that helpful?
So you were just looking at the time series of generation without actually using the weather data?
Yes, so time series of weather data which was measured in the past. So not taking the weather predictions, but only the like this hour, past hour, and past 6 or 8 hours. So feeding all that to a recurrent neural network to predict from t+1 and forward. So you see what I'm saying, like the weather predictions weren't used. So t+1, t+2, weather predictions weren't there. It was just measured meteorological variables which were used to train the network to predict solar generation or solar irradiance based on that.
And how far in advance were you predicting?
So this was like 1, 2, 3, 4 hours using a single model, like sequence to sequence model using LSTM, but yes, the farthest was t+4.
Thank you.
If there are no other questions, feel free to reach out to me if you're interested in working on some solution using data science for energy systems. Always happy to chat.